And the previous class, yesterday's class, electrochemical cells completed. And today's class will start this electrolytic cells. So we take one example, electrolysis of electrolysis of molten and molten and aqueous sodium chloride. Once again, what is the compound formed in this reaction? If you use a molten or aqueous molten NaCl, molten NaCl is dissociated into Na plus and Cl minus. And here at cathode, what is cathode? Negative electrode. So sodium ions accept electrons from cathode and deposited on cathode as sodium. And anode in electrolytic cells, anode is positive and Cl minus involved in de-electronation or oxidation reaction by losing of electrons. So in this anode, chlorine gas is evolved. If you use a molten NaCl, but if you use aqueous sodium chloride, what is the reaction? Use aqueous sodium chloride. What is reactions takes place at cathode? Cathode sodium ions accept electrons and it gives sodium. At the same time, in aqueous water also present, water accept electrons and it is converted into H2 plus hydroxyl ions. So hydrogen gas is evolved in this reaction. And reduction potential of hydrogen is more compared to sodium, or hydrogen is below in electrochemical series. So sodium compared to sodium, hydrogen, water shows more tendency to accept electrons. So instead of sodium, hydrogen is evolved at the cathode. And the same way, what is the reaction takes place at the anode? Anode, again, water, it is converted into O2 plus 4H plus by losing of electrons and also Cl minus, it gives Cl2 by losing of electrons. So oxidation potential of chlorine is more than oxygen evolved here. So in this case, chlorine is evolved at anode and hydrogen is evolved at the cathode. So if you use aqueous NaCl, what are products formed at the cathode? Cathode, that is negative terminal. At cathode, hydrogen gas is evolved. And what are the products evolved at anode? There, which gas is evolved here? Chlorine gas is evolved at the anode. So these are the products evolved that depends on reduction potentials and oxidation potentials of that ions which are evolved at cathode and anode. So we take one more example here. Electrolysis of copper sulfate, aqueous copper sulfate. Here, aqueous copper sulfate electrolysis. In this reaction, what is the reaction takes place at the cathode? Cathode is negative terminal. This copper in electrolyte, when it is liquid state, it is dissociated into copper plus 2 and SO4 minus 2 ions. So what is reaction at the cathode? At the cathode, copper ions accept electrons and deposited as Cu. This reaction is possible. And which reaction is not possible here? Water accept electrons and evolved as H2 plus 2OH minus. This reaction is not possible. And what is the reaction at the anode? Anode, again, what is the reaction takes place here? SO4 minus 2 is converted into S2O8 minus 2 by losing of 2 electrons. And one more also possible. 2H2O gives O2 plus 4H plus 4 electrons. This reaction is possible. This reaction is not possible. Because when reaction takes place, the reduction or oxidation potential should be more. Okay, here accepting of electron, reduction potential should be more. Losing of electron, oxidation potential should be more or less reduction potential. So aqueous copper sulfate, what are the products evolved at the anode and cathode? Products are copper evolved at the cathode and oxygen evolved at the anode. So which product is evolved again? That depends on what is it? Uh, Reduction potentials, and this reaction is possible we use inert electrodes only. What is meaning of inert electrode? Inert electrode means like a platinum, graphite, this type of electrodes, the metals which are below in electrochemical series, then only this type of metals are evolved. So what happens if you use an active electrode? What is the products formed that active electrodes are used? To take an example, copper sulfate solution, that is aqueous. Which electrode is used here? The electrode used is copper electrode is used in this case. What type of products are formed here? At a cathode. At a cathode. Okay. Only copper accept electrons and deposit as Cu. Again, at the anode, the copper rod is the electrode. That copper shows more tendency to lose electrons. So, at the cathode and anode, only copper is evolved when we use copper electrodes. So, when we use the active electrode, that metal only evolved. We take example silver nitrate. If it is electrolyzed, silver nitrate by using of silver electrode, by using of silver electrode. So, what is the reaction at the cathode? Cathode again, silver accept electrons and deposited as Ag. And what is reaction at the anode? Again, Ag loses electrons and converted into Ag plus at the anode. So, how to know which ion is evolved at the cathode or anode? So, here we take one more example. One important reaction, sodium chloride used with the mercury electrode. So what is electrode used here? Mercury is used as electrode. So what is the reaction takes place at cathode? We know that the two reactions are possible when we use an aqueous solution. Here sodium reacts with electron and forms a sodium, deposited as sodium. The same way, H2O also accept electrons and it gives O2 plus H plus and electrons. Sorry, O2 plus OH minus. At anode, that is positive, Cl minus gives Cl2 plus 2 electrons. And H2O, what is the compound here? That is O2 plus 4H plus 4 electrons. In case of anode, this is possible. Okay, in case of cathode, which gas is evolved here is hydrogen gas is evolved here. 2H2O gives H2 plus 2OH minus. This is evolved at cathode, this is evolved at anode. But if you use the mercury, that what is amount of sodium present in that electrolyte reacts with the mercury and sodium amalgam is formed in this reaction. So what is the product formed in this sodium chloride electrolysis? Sodium amalgam is formed in this reaction. Amalgam means any metal when reacts with mercury, that mixture is called as a amalgam. So how to know which ion is evolved at cathode and anode? Here we simple technique we used. Reduction potentials of H2O should be greater than reduction potentials of 1A group, 2A group, and some 3A group elements. So we take example sodium, potassium, or calcium, magnesium, aluminum. These metals are used. So these metals are 1A, 2A group, 3A group elements not evolved, but in this case, if you use aqueous solution, hydrogen is evolved. And next, reduction potentials of H2O should be less than, H2O is less than uh, metals, metals other than 1A, 2A, 3A group, like copper, silver, gold, gold, platinum, or cadmium, zinc, any other metals than 1A, 2A group, 3A group, that metal only deposited at the cathode. Hydrogen is not evolved in this reaction. So, if the electrolyte contains 1A, 2A, 3A group metals, their hydrogen only evolved. If metal contains other than 1A, 2A, 3A group elements, that metal only evolved at the cathode. So after that, next is oxidation potential of H2O. That is greater than. In oxidation means what is that? It loses electrons, so it is greater than if fluorine is present, or SO4 minus 2 is present, SO3 minus 2 is present, NO3 minus 1 is present, S2O3 thiosulfate also present. So here in this case, these ions are not evolved, but O2 is evolved at anode if you use aqueous solution. Same way, if chlorine, here we write oxidation potential of H2O less than chlorine, bromine, iodine ions. So means if these ions are present in that aqueous solution, so here oxygen is not evolved. So which gas are evolved here? Chlorine, bromine, iodine gases are evolved in this reaction. So in this way, we can find out what type of compound is evolved at cathode and anode. Next is, after that we'll start with uh, Faraday's laws. Faraday's laws. What is this Faraday's law? Faraday law explains the qualitative analysis of this electrolytic products. What is amount of product is evolved at a cathode or anode by using of electricity, that is explained by Faraday's laws. So first we start with the first Faraday law. According to first law, when we use a electrolyte electricity, how much amount of substance deposited at the cathode or anode? That is the weight of substance, directly proportional to strength of current in coulombs. So W is equal to weight of substance deposited, and Q is equal to current, strength of electricity or current in coulombs. So according to Faraday's first law, if we pass excess amount of electricity, then more amount of substance deposited at cathode. So W directly proportional to Q, or Q is equal to IT. What is IT here? Current in coulombs is equal to I is equal to current, strength of current in amperes, and T is equal to time in seconds. T is equal to time in seconds. So W directly proportional to IT also we can take, or we put a constant here. W is equal to ZIT also we can use. What is this Z? Z is called as a electrochemical equivalent. That is called electrochemical equivalent. Z, or we can use this W is equal to ZQ. So current in coulombs is equal to W by Z. What it indicates, how many coulombs of electricity pass through that electrolytic solution. Here we write Z is equal to W by Q. Okay. How many coulombs of electricity is passed through electrolytic solution to deposit 1 gram of substance is called as a what is that electrochemical equivalent. Next, here this Z is always equals to capital G by what is that 96,500 coulombs. So 96,500 coulombs is equal to 1 Faraday. So Z is equal to this E is equal to what is E? E is equal to chemical equivalent, and E is always equal to atomic weight by valency of that metal. So Faraday's laws we can write like this also. W is equal to E into IT by 96,500. What is E? E is called chemical equivalent. I is equal to current in amperes. T is equal to time in seconds. 96,500 coulombs is equal to 1 Faraday also. So we write here EIT by 1 Faraday. That is nothing but 96,500 coulombs according to Faraday's first law. Or we write here one more formula. W by W is equal to, we know that we can write EQ by 96,500 coulombs, or we can write weight by equivalent weight is equal to Q by 96,500 coulombs. That is equal to IT by 96,500 coulombs. Okay. So here, gram equivalence of substance deposited is equal to number of Faradays used in that reaction, or number of Faradays passed through that reaction. This is according to Faraday's first law. Once again, number of gram equivalence of substance is equal to n factor into weight of substance. Weight of substance is equal to number of Faradays. What is n factor? N factor in case of acid, that is basicity of acid. So in case of acids, basicity, number of displaceable hydrogens. So n factor is in case of acids, that is basicity of acid, number of displaceable H plus. In case of bases, that is acidity, number of displaceable hydroxyl ions. In case of salts, that is equal to number of positive or negative charges. It is called as a n factor. This is Faraday's first law. And next is second law. Faraday's second law. What is the second law? When different electrolytic cells are arranged in series. This is different electrolytic cells are arranged in series. One electrolytic cell contains silver nitrate. Other electrolytic cell contains copper sulfate. Here we use a inert electrodes, and these electrodes are connected in series. These are connected in series, and same amount of electricity is passed. These electrodes are connected in series and same amount of electricity is passed. So weight of that metal deposited is directly proportional to equivalent weight of that metal. Or weight of silver deposited by weight of copper deposited is always equals to equivalent weight of silver by equivalent weight of copper deposited. This is the second law of Faraday. So next concept is What is meaning of current efficiency? Current efficiency. So what is current efficiency in electrolytic cells? So current used by total current passed through electrolyte into 100. This is called as the current efficiency, or we write here actual actual Faraday's used total number of Faradays of electricity passed. F indicates the Faraday into 100. This is called as a current efficiency. So current efficiency indicates how much amount of electricity is utilized in that electrolysis reaction. And next, so we'll discuss about the conductance. Next concept is uh, conductance, that is called as the electrolytic conductance. So conductor means a medium which allows flow of electrons. So we'll discuss about electrolytic conductance and also electronic conductance. What is meaning of electrolyte? So electrolyte is which is present in liquid state. So we write here liquid state conductor, that is called as a electrolyte. So liquid state of conductor is electrolyte. And what are the liquid state of conductors? Aqueous acids, aqueous bases, aqueous or molten salts. Molten salts are example for electrolytes. Here, positive and negative ions are formed. These positive and negative ions allows that carry electrons in case of electrolytic conductors. So, what are factors affecting electrolytic conductors? First is the nature of electrolyte. Nature of electrolyte. What is meaning of nature of electrolyte? Strong electrolyte is easily dissociated into ions. Strong electrolyte easily dissociated into ions. So strong electrolyte conductivity should be greater than weak electrolyte. So what is this a strong electrolyte? Strong electrolyte means strong acids and strong bases, strong bases, and salts of strong acids and bases. These are example for strong electrolytes. We know that 1A group, 2A group metals can form strong bases. 5A, 6A, 7A group non-metals can form strong acids. They are easily dissociated into ions and they show more conductivity. Weak electrolytes means any acid if contains a carbon, that is always a weak electrolyte, and bases like ammonium hydroxide, salts like ammonium cyanide are example for weak electrolytes. These are dissociated, not completely, difficult to dissociate, and conductivity is less in case of weak electrolytes. Next is what is the next factor influence about this electrolytic conductors? Electrolytic conductors. Next factor. Next factor is concentration of electrolytes. When concentration increases, ion mobility decreases. So what happened here? Conductivity always decreases with increase in concentration of electrolyte. But if you add water, so dilution increases conductivity. Ions are separated with more distance and conductivity always increases. And next is temperature. When temperature increases, more ions are dissociated. So conductivity also increases. And next, viscosity of the liquid. Viscosity, when viscosity increases, conductivity always decreases. And next is ionic size. When ionic size decreases, then what is that? Solvation increases. What is meaning of solvation? One ion is surrounded by water molecules. So this solvation or hydration, it is called. It depends on size of ion. If you take example, lithium ion is surrounded. This is small in size. Lithium ion is surrounded by more number of water molecules compared to sodium. So lithium conductivity in aqueous solution is less than conductivity of sodium in aqueous solution. So when ion size increases, its mobility decreases. When when ion size decreases, it is surrounded by more number of water molecules. Its mobility decreases. When ion size increases, its mobility increases, and if charge increases, mobility again decreases. So these are the factors affecting electrolytic conductance. Once again, strong electrolyte conductivity is more. If concentration of electrolyte is more, conductivity decreases. Dilution increases, conductivity increases. Temperature increases, conductivity increases. Viscosity increases, conductivity decreases. Ionic size decreases. Then solvation increases, conductivity always decreases. Next is metallic conductors. Next is metallic conductors. So metallic conductors also called as the electronic conductors. Electronic conductors. Again, this solid state of conductors again divided into two types. One is called as the attackable, or we can call it active electronic conductors. Second is called as the inert electronic conductors. So active electronic conductors means all metals are example for active metallic conductors except platinum, gold, or graphite. These are the active electronic conductors which are involved in chemical reactions. Inert means platinum, graphite. These are example for inert electronic conductors. And again, what are the factors influence this uh, electronic conductors here? Temperature increases, conductivity always decreases, and conductivity depends on size of metal also, size of metal also, shape of metal also, structure of metal also. And next, number of valence electrons increases, conductivity increases. And when density of metal density of metal increases, conductivity always decreases. This is a what is the properties of electronic conductors, or we can call it metallic conductors. Electrolytic conductors are in liquid state. Metallic conductors are in solid state, which are in solid in state. Physical state is solid state, and next is we'll start with the conductance according to Ohm's law. What is this? We'll start with the next concept. Concept is conductance for electrolytic conductors. According to Ohm's law, resistance directly proportional to L by A. What is this L? L is equal to distance between electrodes, positive, negative electrode, that is L. A is equal to area of cross section of electrodes, that is called as A. So according to Ohm's law, resistance means which inhibit the flow of electrons, which not permits the flow of electrons. Every substance contains some obstruction to flow of electrons, that is called as the resistance. And what is the resistance? Units is equal to ohm. This is indicated by this symbol, or we can write here ohm. And if you write this, what is that mathematical formula? R is equal to, we write here, rho L by A. What is meaning of this rho? Rho is called as a specific specific resistance, that is called as a rho, or we can call it as a resistivity. This is also called as a rho, specific resistance, or we can call it as a resistivity. And rho is equal to RA by L. Okay, this is a relation between rho with L by A and R. And what are the units of this specific resistance? That is equal to R is ohms. In case of SI units, this is a meter square and meter. So we write ohm meters, or we write here ohm centimeter. This is a units of rho, or we can write here in a small cube with 1 ml of volume. We take example when small cube with 1 ml of electrolyte is present, and distance between electrolyte also fixed here. One is positive electrode, one is negative electrode. Distance also fixed. Electrolyte, what is the amount of electrolyte is present? That is 1 ml. We take example. Means volume also fixed. Distance between electrodes also fixed. Area of cross section also fixed. But we don't know concentration here. How much concentration is present, which is not fixed. Once again, distance is fixed. Area of cross section of electrodes fixed. Volume is fixed, but we don't know concentration. So in this electrolyte, what is resistance is called as a specific resistance. And next is after specific resistance, next is conductance. Conductance. First, we start with specific conductance. Specific conductance, or we can call it as a conductivity also, or we can call it as conductivity. So this is denoted by K, that is called as a kappa. Conductivity is denoted by kappa. Here kappa is equal to K is equal to 1 by rho. 1 by rho means we can write here 1 by R into L by A also. So 1 by R, that is called conductance. What is this? It is called conductance. Conductance is always equals inversely proportional to resistance. Again, conductance units reciprocal of ohm or Siemens. Siemens is denoted by S, or we can call it mho also. Reciprocal of ohm, Siemens or mho. So conductance is equal to 1 by resistance. So here K is equal to 1 by rho. Specific conductance is equal to 1 by rho. G is the conductance and this is conductivity, or specific conductance, that is equal to 1 by rho. 1 by rho is equal to 1 by R into L by A, and this is called as a conductance. L by A is called as a cell constant. So that is indicated by G star. G star is equal to cell constant. Cell constant is fixed for any electrolytic cell, and we cannot find out what is that theoretically by calculation. We can find out experimental by indirect methods only. So G star is equal to L by A. So L by A is called as a cell constant. Once again, L is equal to distance between electrodes and A is the area of cross section. So what is this K here again? We take this cube, and here electrodes are present with what is that fixed cell constant, and area means the area of cross section is fixed, distance between electrodes fixed, and concentration is not fixed again, but volume is fixed. Then the conductance is called specific conductance and resistance is called specific resistance. Again, specific conductance is always equals to conductance into conductive. What is the conductance into cell constant? Cell constant is indicated by G star. That asterisk is indicated on upper part of G. L by is called cell constant. We cannot find out by calculation. We can find out L by A by experimental indirect methods only. What are units of this kappa? Kappa units is here we write 1 by R is equal to reciprocal of ohm, reciprocal of ohm. L by A is equal to, we can take L is equal to meter and meter square in SI units. So we write here reciprocal of meters or centimeter or Siemens per meter or Siemens per centimeter also we can use per kappa. And G is equal to Siemens or reciprocal of ohm per conductance. So this is a conductance and the difference between cell constant. So next concept is how to find out cell constant because it is experimentally determined. So G star is cell constant, that is L by A. So methods to find out cell constant of electrolytic cell. We know that here we take an example, potassium chloride solution. That is standard potassium chloride solution. Here two platinum electrodes are used. Two platinum electrodes and distance. This is L. And what is this? This is called as the area of cross section. And what is electrolyte is used in this standard KCl. Standard KCl for this, what is that? K is known. Specific conductor is known of this solution. This is used. With the help of this, we can find out cell constant and it is connected to Wheatstone bridge. This is a standard KCl solution which contains a platinum electrodes. We don't know L and A, but we know kappa value, specific conductance value. So how to find out a cell constant with the help of this? For this, we use a Wheatstone bridge. So what is this Wheatstone bridge? Contains a potentiometer here. This is the resistance. Again, here also resistance is present. And again, here also resistance. Here also resistance. And what is this? It is a Wheatstone bridge. This is we can take it as R2, R1, R3, R4. We take it as like this. Okay, here we take R4 and we take it as R3. So R2, what is R2? R2 is connected to what is the standard KCl cell. What is that? It is a KCl host case. We know that. That is R2. R1 is variable. We can change. R3, R4 known resistance. R1 is variable. Variable means we can change so that in this potential in this Wheatstone bridge at a null point is obtained so that the null point the distance what is the sound is minimum, so we can adjust this variable resistance to get that null point. So at null point we can find out the R2 value. Here we use this method R1 by R2 is equal to R3 by R4. R1 is equal to variable resistance, R2 is equal to, it is connected to standard potassium chloride electrolytic cells. R3, R4 are, what is that, known resistance. So from this we can find out resistance of potassium chloride standard solution. R2 is equal to R1 into R4 by R3. From this we can find out what is that R2 value. If you know R value, if you know K value, then we use this equation. K is equal to 1 by R into cell constant, that is L by A. and cell constant is equal to K into R. From this, what is that? Resistivity, specific conductance and also resistance. We can find out cell constant value that is equal to L by A. This is a method to find out cell constant experimentally. Next concept is molar conductivity. So what is this? It is called as a molar conductivity. This is a symbol of conductivity and it is a molar conductivity. We take an example, one cube. One cube, again, conductance is called conductivity. This is called specific conductance in a small cube. Here, volume is fixed in this small cube. But if this volume increases, then what happens? If volume increases and concentration is also, we know that is one molarity. Okay. If we take concentration in molarity, we know the concentration, but the volume increases, that conductivity is called as a molar conductivity, that is always indicated by K into V. What is meaning of molar conductivity? Conductivity of 1 mole of electrolyte is present in electrolytic cell, and distance between electrodes, uh, area of cross section is large enough so that total electrolyte is accommodated. Total electrolyte we can place between these electrodes. Means here in this molar conductivity, volume is not fixed. Volume is unknown. We don't know that volume. Area of cross section also fixed. Length also, area of cross section is not fixed. Length is not fixed. So in between the distance is large enough so that total electrolyte is accommodated. So this is called molar conductivity. Molar conductivity of that electrolyte. So molar conductivity is equal to uh, K into V. K is called as a what is that? Specific conductance. V is equal to volume. So volume is large enough here, and we know that concentration in concentration in molarity, that concentration in molarity always equals to number of moles into 1000 by volume of solution in milliliters. If electrolyte is 1 mole we take, then what is this molarity? Molarity is equal to 1000 into 1 by volume in milliliters. So what is this volume in milliliters? That is equal to 1000 by molarity. So molar conductivity we can write like this also. Molar conductivity is equal to K into, instead of V, here we know that K into V, or molar conductivity we can write like this also. Molar conductivity is equal to K into 1000 by, what is the concentration of the solution in molarity. This is called molar conductivity. And next concept is equivalent conductivity. What is this equivalent conductivity? Next concept is equivalent conductivity. Here, equivalent conductivity is equal to K into volume. So, what is this in equivalent conductivity? We take 1 gram equivalent of, so for this we use 1 gram equivalent of electrolyte. That conductivity is called equivalent conductivity, or we write here equivalent conductivity is equal to K into 1000 by normality also we can take. So normality we can take it as a concentration is C, that is called as a equivalent conductivity. What are the units of molar conductivity and equivalent conductivity? So here equivalent conductivity is equal to Siemens centimeter square per gram equivalence, reciprocal of gram equivalence And molar conductivity unit Siemens centimeter square. What is that? That is number of moles, reciprocal of number of moles. So what is difference between molar conductivity and also equivalent conductivity? Molar conductivity by equivalent conductivity is equal to concentration according to normality by concentration according to molarity also. Or molar conductivity is equal to n into n factor into equivalent conductivity also we can take. This is relation between molar conductivity and also equivalent conductivity of that electrolytic solution. Next is what is the effect of dilution with molar and equivalent conductivity. Here, molar conductivity, and this is the conductance, and this point indicates at infinite dilution. This point indicates at infinite dilution. Infinite means we add excess amount of water, final water, so that conductivity does not change at that excess amount of water is added. This is called infinite dilution. At infinite dilution, this is the conductivity indicated. When you compare with molar or equivalent conductivity with conductance, so here we get this law for weak electrolytes that is equal to CH3COOH. For strong electrolytes, we get this, that is potassium chloride. So what it indicates, for strong electrolytes at infinite dilution, up to infinite dilution, ions are dissociated. For weak electrolyte, it is not possible at up to infinite dilution that ions are dissociated. So for strong electrolyte, here for strong electrolyte, molar conductivity is equal to molar conductivity at infinite dilution minus B by root C. So what is this? B indicates B is the constant. It depends on electrolytes. Dilution once again. At infinite dilution, we add excess amount of water so that total ions are disappeared. So total electrolyte is dissociated into ions at infinite dilution. And with increase in dilution, with increase in dilution, with increase in dilution, molar conductivity or equivalent conductivity increases. But specific conductivity always decreases, because specific conductivity means in a small volume, when we increase the dilution, number of ions in that small volume always decreases. So less ions are present in that small volume. So K decreases, but in case of molar or infinite conductivity, equivalent conductivity, so what is that? There is no fixed distance and no fixed volume. So when volume increases, ions are more dissociated and they show more conductivity. And next is for weak electrolytes. For weak electrolytes, how to find out for weak electrolytes, how to find out conductivity? We use one law that is called as a, what is that? It is called as a Kohlrausch law. Kohlrausch law is used to calculate conductivity of weak electrolyte at infinite dilution. Here, according to this Kohlrausch law, conductivity at infinite dilution, if you take molar conductivity, that is equal to number of cations into conductivity of cations plus number of anions into conductivity of anions, according to Kohlrausch law. or conductivity at infinite dilution of MgCl2, that is equal to how many magnesium ions are present? One only. So conductivity of Mg plus 2 plus what is that? The conductivity of Cl minus. How many are there? Two are there. Conductivity of Cl minus at infinite dilution. From this, we can find out alpha also. Alpha is called as the degree of dissociation. So according to alpha, conductivity by at a particular concentration by conductivity at infinite dilution, that is called as a alpha value. Conductivity at particular concentration by molar or ionic equivalent conductance at infinite dilution, that is called as a degree of dissociation. This is one application of Kohlrausch law. And one more concept is ionic mobility. Ionic mobility. Here, ionic mobility, according to this, any conductance directly proportional to mobility of cations, speed of cations, and mobility of anions also. So, conductivity of positive ions directly proportional to mobility of cations, conductivity of anion directly proportional to mobility of anions. Or conductivity of cation is equal to number of Faradays into total mobility of cations, and conductivity of anions is equal to total number of Faradays into mobility of anions again. So here ionic mobility, what is ionic mobility? That is equal to ionic velocity by potential gradient. This is called potential gradient. Or what is meaning of potential gradient? Potential gradient is equal to potential difference in volts, potential difference in volts by electrode separation. Electrode separation, that is called as a potential gradient. So in this way, we can find out ionic mobility also. And we'll discuss one example for Kohlrausch law, how to find out conductivity of weak electrolyte. Here, conductivity of acetic acid, how to find out? We know that acetic acid is weak acid. It is not completely dissociated. Again, conductivity depends on how many ions are present in that electrolyte and the speed of the ions. But here we cannot find out exactly how many ions are dissociated, because in this case the dissociation is less. Means if we take 100 molecules of acetic acid, only in that 100 molecules only 5 to 10% only dissociated. Means here CH3COH, if we take 100 molecules, the equilibrium is formed here CH3CO minus and H plus in presence of water. If we take 100 molecules, up to 95 molecules only undissociated, 5 molecules only dissociated, and 95 up to 95 molecules are undissociated. So we can find out conductivity of that electrolyte based on ions. Remaining part, it is not possible to find out conductivity. So for this electrolyte, how to find out this conductivity? By using of Kohlrausch law. So we take an example, conductivity of sodium acetate, it is a salt, and sodium acetate is completely dissociated into acetate ions and also sodium ions. Because this sodium acetate, this is strong electrolyte, it is completely dissociated. And in the same way we take HCl, it is also strong acid, so it is dissociated into H plus and also Cl minus completely. If we take NaOH, it is also dissociated into Na plus and also OH minus completely. So we use this equation. Conductivity of acetic acid is equal to conductivity of sodium acetate plus conductivity of HCl minus conductivity of NaCl. So from this we get conductivity of acetate ion plus conductivity of sodium ions plus conductivity of H plus ions plus conductivity of Cl minus minus conductivity of Na plus minus conductivity of Cl minus. It is cancelled and we get conductivity of acetate and also H plus ion. So based on this, what is the relation? With the help of this strong electrolytes, we can calculate conductivity of weak electrolytes by using of Coal-Dash law. So this is the electrochemistry second part, electrolysis part completed according to exam view, and we'll discuss few questions based on this electrolysis. Here one question. Here if you use the K2SO4 aqueous, and if you use calcium iodide, that is also aqueous. Copper bromide, that is aqueous. Copper chloride, that is aqueous. And next is copper sulfate, that is also aqueous. Potassium nitrate, that is also aqueous. So find out what are the cations and anions are deposited at an electrode. Find out this. What are cations and anions deposited in in case of potassium sulfate, we know that when 1A, 2A group, 3A group metals are present, hydrogen is evolved at cathode. We know this. So sulfate ions are present, oxygen is evolved at cathode, and hydrogen is evolved at anode. We take calcium iodide aqueous solution. So again, calcium is second A group element. Hydrogen is evolved at cathode, oxygen evolved at anode. If we use calcium iodide, iodine is evolved at cathode, anode, and calcium is evolved at cathode. Copper bromide. Bromine is evolved at anode and copper is deposited at cathode. Copper chloride. Copper is deposited at cathode, chloride is evolved at anode. Copper sulfate. Again, copper is deposited at cathode. Instead of sulfate, oxygen is evolved at anode. Potassium nitrate. Potassium hydrogen is deposited at, or evolved at cathode. Instead of nitrate, oxygen is evolved at anode. So this is the method to find out what type of ions are evolved at cathode and anode. So what is that? Next, we'll take one more example. One more example here. How much charge is required? How much charge required? Required to required for first one is to convert 1 mole of, to deposit 1 mole of Al plus 3 to Al. Second is 1 mole of MnO4 minus 1 to Mn plus 2, and 1 mole of Cr2O7 minus 2 to Cr plus 3, 2 Cr plus 3. Find out. So here, aluminium plus 3, it requires 3 electrons, means 3 moles of electrons. 3 moles of electron charge is equal to 3 Faradays. So it is converted into Al. So how much electricity is required here? 3 Faradays strength of electricity is required to deposit aluminum with plus 3 charge And MnO4 minus 1 to Mn plus 2. MnO4 minus 1. First, you find out oxidation state of manganese. X is equal to, we can take it as X plus 4 into minus 2 is equal to total charge is minus 1. X is equal to, we get plus 7. So MnO4 minus 1, charge is plus 7. This is plus 7, Mn plus 2. So how many electrons are changed here? 5 electrons here. So how many Faradays are required? 5 Faradays are required. In the same way, Cr2O7 minus 2 to Cr plus 3. Cr2O7 minus 2 to 2 Cr plus 3. Here, oxidation state is plus 6. Here, 2 3 is the plus 6. 2 6 is the plus 12. What is that? How many Faradays are required for this? The difference is the 6 electrons. So 6 Faradays are required for this deposition. So in this way, we can find out